Here are some of the basic log and exponential facts that tend to be relevant in Chapter 1. If you're looking at the graph of, say, y equal e to the x, we're modeling exponential growth, so the pattern is pretty easy to remember. When x is 0, y is 1, and there's exponential growth, so as the x's get bigger and bigger, the corresponding y's on the graph get bigger and bigger. And that says as x goes to infinity, e to the x is going to infinity. And if you look to the left, as x is going to minus infinity, the graph is settling down with y-coordinates getting closer and closer to 0. That's saying as x goes to minus infinity, that the limit of e to the x is going to be 0. Now, the graph of y equal to log of x is essentially the same graph as the graph of y equal to e to the x, except that the x and the y have exchanged roles. So instead of going through the point 0, 1, we're going through the point 1, 0 with the log of x. And it's a fairly simple shape. What you might notice is that as x goes to infinity, it seems that the y's are getting bigger and bigger at the very least. In fact, as x goes to infinity, the y's can go to infinity also. So that's what we're saying down below here. As x goes to infinity, log of x goes to plus infinity. This could be considered to be a little bit unclear, but certainly x can go to infinity on the y equal e to the x graph. Consequently, the corresponding coordinates on the log graph, the y's, can also go to infinity on the graph. Finally, you notice that as x gets closer and closer to 0 from the positive side, the corresponding points between 0 and 1 on our graph are dipping rapidly down toward minus infinity. So we can sum that up by noting that the limit as x goes to 0 from the positive side of log of x is minus infinity. There are many variations on this theme. For instance, if you look at the limit as x goes to infinity of e to the minus x, little algebra says that the e to the minus x can be replaced by 1 over e to the x. So x is going to infinity. We know that would mean that from above that the e to the x is also going to infinity. If I call e to the x u, then notice that we're saying that as x goes to infinity, u is going to infinity. The 1 over e to the x is 1 over u, and this is the kind of thing that we definitely know is going to give us a limit of 0. Here's another example. We were looking for the limit as x approaches 0 from the positive side of 1 over log of x. Notice that this would mean that as x goes to 0, the natural log of x would be going to, we look above for a reference, still not very pretty. And so if I let u be the natural log of x, then u is going to minus infinity. That's one of the infinities. And the limit as u goes to minus infinity of 1 over u is also going to be 0. And then these sorts of ideas can be applied in various places. All right, here's a more ambitious example. We're looking at a limit as x goes to infinity of, and then there's a bunch of stuff up here where all of it's basically going to infinity in the numerator and in the denominator. We don't know what kind of limit we're going to get in a situation where we have infinity over infinity. We need to do some algebra in order to break things down into pieces that we can work with. So, recopying over here, I decided to multiply by e to the minus 2x over e to the minus 2x, pretty much for the usual reason I want to get nice pieces where I'm getting, as I multiply things out, limits that are going to be constants. So e to the minus 2x times e to the 2x is going to give us 1. The e to the x times e to the minus 2x, that's going to be e to the x minus 2x is going to be e to the x minus 2x gives me minus x. That's what I'm having us note here. Similarly, if we multiply things out down below, this times this gives me another e to the minus x. This times that gives me a minus 1. And finally, I see that as x goes to infinity, these are nice pieces of the sort that we were just looking at. This goes to 0, this goes to 0. So the limits for each piece, 1 plus 0, 0 minus 1, simplifies to minus 1. All right, now it's time to talk about what I'm calling the big fact about E. It's a maybe more striking fact to me than it might be to someone else. The way that I first saw calculus being developed, this was not introduced until quite a bit later, when you could actually justify that there was some number E out there for which this would be true. And I have no good way of providing you any evidence that such a thing should be true, using things that you would have learned up through pre-calculus. The book, in fact, has us notice that, in fact, this is going to be true whether it's plus infinity or minus infinity, which kind of caught me by surprise when I was first trying to verify it. Here is the complete calculation that the limit as x goes to minus infinity will also give you E. You can peruse it at your leisure. I'm mostly interested in just establishing the limit fact here, but it is a nice example showing how that algebra can be used as a tool to uncover information that we would like to access. Here's something more along the lines of what you would be expected to be able to do. All right, looking at the problem here, the main difference is the 3 that I inserted here in the exponent. A property of log says that if you have something to a power and then raised to a further power, this is a situation where you get the same answer by multiplying the exponents. If you look at what we have here, here's the multiplication of the powers. I'm breaking it up into a nesting of powers, first with respect to x and then my power of 3. And then when we look at what's happening inside here, that's going to E, which means that the limit is basically complete. This has to be getting close to E cubed. The little bit of algebra that we used here is the main trick that we need to be able to use in order to be able to plug into our so-called big fact to get answers of interest to us. All right, here's another example. Main thing that changed compared to the original fact was the placement of the 3 here in place of the 1. Now, ultimately, you want to look over here, I need to see something like a u going to infinity with a 1 plus 1 over u to the u power in order to be able to do anything useful. So running back to the original expression here, I need to have that 1 in the numerator. I can get that done by re-expressing the 3 over x as 1 over the quantity x over 3. If you take the reciprocal of x over 3, you're getting the 3 over x. That's the big new step here. Now I can replace the x with an x over 3 times 3, and then use the earlier trick to insert an extra parentheses here so that we have stuff to a power raised to a further power. That x over 3, I can make that a u. So now I have 1 plus 1 over u to the u power, then raised to the third power. We're done. Stuff inside here is going to e, and we see our familiar e cubed as an answer here.